G'day, thanks for joining me as we conclude our Equilibria unit today with a lesson entitled Solubility Products, the Common Ion Effect and Partition Coefficients, where we're going to understand and apply these concepts, the solubility product, the common ion effect, and the partition coefficient to a system that's at equilibrium. So to finish off, we're going to look at the concept of dissolving. We looked previously at how ionic compounds dissolve into a solution. We've talked about the idea that solubility is all relative. Even the most insoluble compounds are still dissolving a very tiny amount, which for all practical purposes, might be able to be categorized as insoluble. But even something like mercury sulfide, we have, a really, really tiny amount that's still able to dissolve in a given volume of solvent at a given temperature. So when we were looking at this last time, we were talking in terms of enthalpy changes, looking at how the delta H of hydration, the lattice energy, and the delta H of solution all can interplay with one another to determine how ionic compounds in their solid form go to ions in an aqueous form. So look, we've got a video on that previously there if you want to recap. What we're going to look at today is we're going to look at this system, in this process of dissolution through the lens of equilibria. So let's remind ourselves about a few concepts. We have a saturated solution where we have the maximum amount of solute dissolved in a given solvent. At this saturated solution, we have an equilibrium being established between a saturated solution and the undissolved ionic compounds. So, you imagine that we've got a certain ionic compound, which I'll draw, representing my ions there. So, we have an ionic solid like that, that goes on all back through there. There's a equilibrium occurring where we have our compound in the solid form and an equilibrium is established between the solid ions and the aqueous ions. So, if we imagine that's my solid, that's my AB solid, in a saturated solution, an equilibrium is established where you have certain ions moving out into, the dissolved into the ions in the aqueous phase, where we're going to have, the positive cation aqueous and the negative anion aqueous like that. And then similarly, we're going to have, in this equilibrium, we're going to have the aqueous ions moving back to the ionic solid. So at the equilibrium position, we have the rate of the solid ions going to the aqueous ions equaling the aqueous ions going back to the solid ionic salt. Rate of the forward and backward reactions are equaling each other, so there's no observed change. So the equilibrium established between the saturated solution and the undissolved ionic compound. The rate of ions solid turning into aqueous ions equals the rate of aqueous ions turning back into the ionic solid. So as we have an equilibrium here, we can write an equilibrium expression to express this. As with all of our equilibrium expressions, it's a ratio of the concentration of products over the concentration of reactants, taking into account the stoichiometry, raising it to the powers as we need to be. Now in this instance, we have two aqueous, but we also have a solid. We can ignore the solid in our equilibrium expressions because the concentration of solids is constant. So as such, we can write a expression of our equilibrium up here as a K value for the solubility product, where the solubility product is the concentration of our two ions in the aqueous solution raised to the power of their stoichiometry, where the stoichiometry is going to be dependent on the charge of these ions, as we'll see in just a second. So this is just another equilibrium expression. We're just ignoring the ionic solid there because it's a solid. So, for example, what would an equilibrium expression for calcium phosphate look like? Let's go through. If that's one you want to have a go at, feel free to give it a pause. But we can consider our, our equilibrium up here for calcium sulfate. Was it calcium sulfate? It was calcium phosphate. So calcium's a 2+ ion, and we're going to have our phosphate as a 3- ion. So we're going to have Ca3PO4 2, like that. So that's going to be our ionic solid there on the left-hand side. In a saturated solution, we have an equilibrium being established between our calcium ions and our phosphate ions, where these are both going to be aqueous, like so, and we've got to take into account the stoichiometry. So we're gonna have 3 of them, we're gonna have 2 of them. So look, to write an expression for the solubility product here, our KSP is going to be equal to the concentration of calcium 2 plus to the power of 3 raised to its stoichiometric coefficient multiplied by the phosphate ion raised to the power of 2. So that there is our equilibrium expression for this calcium phosphate. So as you might be able to see where we're going, if we've got some values, if we've got some equilibrium constants, if we've got some concentrations, we can start to calculate some values here. But yeah, there you go. The KSP is Ca2 plus to the power of 3, the concentration thereof, times by PO4 minus to the power of 2, just like any other equilibrium expression, and we're ignoring that ionic solid. So let's go into that. Let's go into some calculations here. Solubility products only apply to ionic compounds that are slightly soluble. This is as ion interactions in soluble compounds interfere with the simple equilibrium that we're assuming in this case. You know, we're assuming a pretty simple equilibrium there, whereas the more highly soluble ones, unfortunately, aren't that simple. So look, we're just applying this to our slightly soluble compounds. Needs to be a saturated solution at 298 kelvins. That solubility is going to change with temperature. So when we're quoting KSPs, we have a saturated solution at 298 Kelvin. And as with any equilibrium constant, which this is, the position is going to imply the solubility. You know, the larger that number, the more that equilibrium is pushed over to the right-hand side, the more the ions are dissolving. So the larger that value, the more soluble it is. The smaller that value, the more that equilibrium is to the left-hand side, and thus the less soluble, the more it's in that ionic solid there. What else? Units for equilibrium constants need to be determined for each case, just as we've been doing for all of our equilibrium constants. It's going to be dependent on you know, how many powers we have there and what we're multiplying together. So mixing together 2 ions whose product of the concentration exceed our solubility product results in a precipitate. So we can start to use these values to infer if we're going to form a precipitate based on what values we have for concentration and what that KSP is. So let's run through a few examples here. Let's first of all look at how you can calculate the solubility product from the solubility of a substance. So what we need to do is we need to use stoichiometry to determine the aqueous ion concentration from the ionic solid, and then use the KSP expression. So in this instance, all we're really doing is sort of plugging and playing with our equilibrium expression that we're going to express once we've got the equilibrium equation. So for example, determine our solubility product for a solution of calcium fluoride that has a solubility of that many moles per decimeter cubed. If you want to pause and give it a crack, as always, it's a great idea. Let's have a look through it. So if we scroll down a little bit, we had, what was it? We had calcium fluoride. So let's write an equilibrium expression here for calcium fluoride. If we're going to have, you know, Ca2 plus, F minus, so CaF2 in the solid, it's going to be at equilibrium with Ca2 plus 2 F minus, both of those in the aqueous phase like that. So if we're writing an equilibrium expression here, our KSP is going to be concentration of the Ca2 plus, stoichiometric coefficient just 1, so to the power of 1 is itself, multiplied by the F minus to the power of 2, because we have that stoichiometry to take into account. All right, now what were we given? We were told that calcium fluoride has a solubility of 2.15 times 10 to the minus 4 moles per decimeter cubed. So we can use some simple stoichiometry to work out the concentrations of those two there, and then we can just plug them in. So if we have a solubility of that as that value there, well, the concentration of our calcium ions is just going to be that 1-to-1 mole ratio, because for every one of those we have one of those, whereas our stoichiometry for a fluoride is going to be a 1-to-2. So we're going to have 2 times that value for the fluoride. So we can just go ahead and plug these values in, which I might move down here. Our KSP, like I said, our concentration of the calcium ions is just going to be equal to that value there. Not minus 14, way too small. Minus 4 there, because the 1-to-1 stoichiometry to the power of 1. And then we're going to multiply it by twice as much, because for every one of those, we've got 2 fluorides. So it's going to be 2.15 times 10 to the minus 4 times 2. And then we've got to square that from our KSP expression. And then we can go ahead and plug all of this in the calculator to get our equilibrium constant, to get our solubility product here. So 2.15 times 10 to the minus 4 times by 2.15 times 10 to the minus 4 times 2 squared. That will give us a value of 3.98. Do it to 3 significant figures, times 10 to the minus 11. And then we've got to work out units as we do. So let's consider this. We have a moles per decimeter cubed, and then we got multiply that by a moles per decimeter cubed squared. So a moles per decimeter cubed times a moles per decimeter cubed. So we're going to end up with units of mole to the 3. So we've got 3 of them. Decimeter cubed to the minus 12, like that for our KSP value here. So there we go. The KSP is 3.98 times 10 to the minus 11 moles per decimeter cubed. So what we can do with this expression, or with this value rather, is that if we have concentrations of our calcium and fluoride, if we have the product exceeding our KSP value down there behind my face, then we can predict that a precipitate is going to form. Whereas if it's less than that, we can predict that the precipitate will not form. So let's go the other way. Let's say if we wanted to calculate the solubility, but we're given the KSP value, what would we do in this case? Determine the equilibrium expression in terms of a single ion, substitute in KSP, and then rearrange to calculate the solubility. So let's have a talk about what we can do here with an example. Determine the concentration of silver ions in a saturated silver carbonate solution where we're given the KSP value. So let's go ahead and write the equilibrium that's been established. So we have silver carbonate, so Ag2, CO3 solid, equilibrium with 2 Ag plus aqueous and CO3 2 minus aqueous. So we can write the solubility product expression where the KSP is going to be the concentration of our silver ions squared multiplied by the concentration of the carbonate ions, and we're given the KSP value this time. So what's our KSP? 6.3 times 10 to the minus 12. All right, let's not worry about units because we're just going to plug it in as a number. So let's go ahead and let's consider about how we can get this as a single, how we can express it in terms of a single ion using some stoichiometry. So let's say if we have our concentration of carbonate ions. So let's just say if carbonate ions equals X, therefore our concentration of silver ions is going to be twice as much. You know, you got the mole ratio of 1 to 2, 1 carbonate, 2 silvers. So let's say that is 2X. Now let's get a little bit algebraic with it. We got a concentration of silver ions, which is 2X. We're going to square that, and then we're going to multiply it by X for our carbonate. So we're expressing the KSP in terms of just one unknown variable, which we can do from the stoichiometry. So, you know, we expand that, we end up with 4X squared that we're going to multiply by X. So that's going to end up with 4X cubed. And we've got our KSP value. So 4X cubed equals 6.3 times 10 to the minus 12. So we'll do a little bit of rearranging here, a little bit of mathematics just to rearrange, get X, and we'll end up with a concentration for our carbonate ions, which we can then calculate what the question asked for, which was the concentration of the silver ions. So let's do that. So let's say if we want to get X cubed, we can get our value 6.3 times 10 to the minus 12. We can divide that by 4. That'll give us a value of 6.3 times 10 to the minus 12 divided by 4. We got a value of 1.575 times 10 to the minus 12, which if we want to get X, we can get the cube root of that value there. Let's see if I can get a nicer cube root sign. That'll do. So I got the cube root of my answer, and we end up with a value of, for X, which is 1.16 times 10 to the minus 10 to the minus 4 moles per decimeter cubed. But we've got to make sure that we're answering our question, because our question was asking us for the concentration of silver ions. Remember that our X is representing our concentration of carbonate ions. So to get the concentration of silver ions, Ag plus is going to be 2 times our answer up there, 2 times 1.16 times 10 to the minus 4, which I'm going to multiply my answer by 2. We end up with 2.33 times 10 to the minus 10 to the minus 4 moles per decimeter cubed. And if we go back over here, that will be our answer there, 2.33 times 10 to the minus 4. So 2 types of calculations. We can go from the solubility given the KSP or the KSP given the solubility, depending on what we need to do. All right, let's look at something which affects this, which is called the common ion effect. This describes the decrease in solubility of a dissolved salt by the addition of a soluble compound with an ion in common with the dissolved salt. So the common ion affects the equilibrium position of the dissolved salt. So what this is saying is if we've got our solubility product here, but let's say I chuck in another salt there, which is, Cb, and then I've got C plus ions and B minus ions. Well, they're the same kind of B minus ions, aren't they? So that's going to change the concentration of our certain ion, the common ion that is in common with the 2 salts. So this often results in a precipitation, because what we're going to do is we're going to affect that position of equilibrium. If you're putting a common ion, you're increasing the concentration of one ion. The Chatelier's principle, that good stuff, we're going to move equilibrium one way or the other accordingly. Consider a saturated solution of barium sulfate, where we have our equilibrium occurring there in the saturated solution. Sodium sulfate is then added to this solution with a common sulfate ion. Sodium sulfate, salts are very soluble. So what's going to happen? This would shift the position of equilibrium above to the left as the sulfate has increased. So we imagine sodium sulfate, very soluble, forms all sodium and sulfate ions, or at least a large amount. This sulfate ion is in common. So essentially what we've done is we've increased the concentration of the sulfate ion. The Chatelier's principle, the equilibrium wants to re-establish the equilibrium. So we're going to push the equilibrium to the left-hand side. So this common ion shifts position of equilibrium to the left. What does this do? This is going to precipitate out barium sulfate, because we're making more of the solid barium sulfate when we shift that equilibrium position. We can also think of this in terms of KSP. So if we write the KSP expression here, equals Ba2 plus times by SO4 2 minus. The product of the 2 ions now exceeds its KSP. We've increased the concentration of the sulfate. We had a saturated solution, so if we increase that, this number becomes bigger, which exceeds the KSP, so a precipitation occurs. Our sodium sulfate there, obviously meant to be Na2SO4, point all still stands. Here's a question. Use your words. Predict how the solubility of calcium hydroxide in water compares to its solubility in aqueous sodium hydroxide. Explain your reasoning. We'll go through the answer now. So let's write a couple of equations here. If I go down and let's first of all write an equation for calcium, calcium hydroxide in water. So calcium hydroxide like that, it's going to be Ca2 plus, that'll be solid, Ca2 plus aqueous plus 2OH minus aqueous like that. We've got an equilibrium there, we're in a saturated solution, but then we add some sodium hydroxide, NaOH. This will dissolve and will form sodium ions and hydroxide ions. What do we have? We have a common ion. Common ion being the hydroxide ion in this instance. So what is this going to do? This is going to increase the concentration of the hydroxide. The Chatelier's principle, if we increase the concentration of the hydroxide, the system wants to re-establish equilibrium by decreasing the concentration. It's going to drive that top equilibrium, push it to the left-hand side to favor the reactants. We're going to have some more calcium hydroxide precipitate out of the solution. So what have I written here? Solubility decreases due to the common ion effect. Increase in the hydroxide ions from the sodium hydroxide pushes equilibrium further to the left. We can also think in terms of that solubility product. The product of our two ions now exceeds the solubility product because we've increased that value for hydroxide. So that number is of course going to be larger. Fantastic. Final thing to look at in this unit is another type of equilibrium expression, what's called the partition coefficient. This is describing the ratio of solute concentration between two immiscible solvents at equilibrium. So consider shaking an aqueous solution of a substance with an organic solvent. We can represent our equilibrium that occurs like this, where X is whatever our substance is, it's going to have a certain solubility in the aqueous layer, it's going to have a certain solubility in the organic layer, all dependent on its properties. Compound has a certain solubility in water and another certain solubility in the organic layer. Particles cross the boundary between the liquid layers until an equilibrium establishes, where the equilibrium expression represents the partition coefficient. So, if you imagine the classic separating funnel, I'll draw a little picture here. That's my little separating funnel. Let's just say we had two layers. I'll even put a little top there, a little stopper in it. Look at that, what a piece of art. So, we've got two layers, two immiscible layers, and we have a certain substance. There's an equilibrium at the partition of these two layers. So an equilibrium is established as the substance moves between those two layers depending on its solubility in each. Particles cross the boundary between the liquid layers until an equilibrium establishes, where the equilibrium expression represents the partition coefficient. Why don't you see if you can write a general partition coefficient equilibrium expression based on that equilibrium there. As with all equilibrium expressions, it's products over reactants. It'll look something like this. So it's going to be the concentration of X in our organic over the concentration of X in our aqueous. Now just bear in mind, I could have started in the organic and I could have added the aqueous. Just make sure, in which case, they would be flipped if I did an equilibrium expression for that, as long as your partition coefficient is consistent with your particular equilibrium that you've written there. So our equilibrium expression is constant at a constant temperature. And this helps to explain why we can separate mixtures in chromatography. An equilibrium between the partition of the mobile and the stationary phase as the chromatography proceeds. Chromatography being used to separate it. There's a certain affinity the substance will have for the mobile phase, for the stationary phase. So this is all explained in terms of these partition coefficients. The greater the solubility in the mobile phase, the faster it moves through the system. So let's finish up with some calculations using our partition coefficients. Again, our size is determined by the relative solubility of the solute between the two solvents. If I have my partition coefficient for this one above, a very large value, tells me there's much more in the organic layer. So it tells me it's more soluble in the organic layer. A very small partition coefficient in this instance is going to tell me it wants to be in the aqueous layer. So we can draw inferences about its properties. Think back to the idea that like dissolves like. Non-polar substances dissolve non-polar substances. Polar substances dissolve polar substances. So, if our KPC, if our partition coefficient value is telling us it wants to be in the aqueous phase, that's implying that it's going to be a polar substance. Likewise, if it's telling us it's, favoring being in the organic layer, then that's going to tell us it's a non-polar substance. In this instance, our units are going to cancel out when calculating the partition coefficient. We're going to have a moles per decimeter cubed for the organic layer, a moles per decimeter cubed for the aqueous layer. That's going to cancel out. We're going to have no units. And in fact, because it's canceling out, it's not too important what your units of concentration are going to be here, because they're going to cancel out as long as they're the same thing. So just make sure they are consistent with one another. Let's finish off with the question. 0.034 moles of an unknown compound was dissolved in 0.020 decimeters cubed of an organic solvent before being shaken with 0.050 decimeters cubed of water, where the amount of compound extracted was determined to be 0.032 mole. Determine the KPC value. Let's go through it now. If you want to pause and give it a shot, we can check the answer. So the first thing we've got to do is we've got to write an equilibrium equation. So we have X, we're starting in our organic solvent. So last time we were starting in the aqueous and we're shaking with organic. This time we're starting in an organic solvent and we're shaking with a aqueous solvent. So look, our KPC, our partition coefficient expression is going to be reflecting the process that we've done. So we've got the concentration of the aqueous as the products over the concentration of the organic as the reactants. So what we've got to do is we've got to do two calculations. We've got to get the concentration of X in the aqueous. We've got to get the concentration of X in the organic. And then we'll be able to, I might just fix that up. Then we'll be able to just plug our values in there. So we can just use classic C equals N over V. So let's have a look. What were the number of moles in the aqueous? Our question told us that it was after being washed, we got 0.032 moles out of the 0.050 decimeter cubed of water. So let's plug those values in there. We have 0.032 divided by 0.050 decimeters cubed. And that will give us the concentration of our substance in the organic layer, which is going to be 0.64 moles per decimeter cubed. And then over here in the organic, well, if we had 0.032 in the aqueous and we started with 0.034, that just means the amount in the organic has to be the difference between those. That's what's remaining. So we subtract those two from each other and we have 0.002 moles remaining. And how much volume of the organic? 0.02. So let me plug that in, 0.02. And that will give us an answer of, I probably could have done it in my head, 0.1 moles per decimeter cubed. So we know how much is in each layer. We can now get the partition coefficient by getting our value for the aqueous, dividing it by the organic. So that's going to be 0.64 divided by 0.1, sorry. And that will give us an answer of 6.4. So what is this telling us about the substance? This is telling us this equilibrium with a large value of 6.4 there is very much over to the right. So it's very much favoring the organic layer. And that makes sense because there's much more in the organic layer compared to the, favoring the aqueous layer. And that makes sense because there's much more in the aqueous layer than the organic layer. So we could make inferences about the polarity of the substance, so on and so forth. But all the question was asking us for was our value for the partition coefficient, which is 6.4. Fantastic. That concludes the lesson. What did we do? We understood and used the term solubility product. We wrote an expression for it. We calculated it from concentrations and the vice versa. We investigated and understood the common ion effect to explain the different solubility of a compound in a solution containing a common ion. And you can do some calculations with the concentration of the common ion as well. We then looked at partition coefficients, state what is meant by the term partition coefficient, calculate and use the partition coefficient for a system in which the solute is in the same physical state in the two solvents, understand the factors affecting the numerical value of the partition coefficient in terms of the polarities of the solute and the solvent used. Task for this lesson, if you want to consolidate, pause one column at a time from the bottom to the top. Fantastic. That concludes both this lesson. It also includes this look at Equilibria that we've been doing. Look forward to next time where we start something new. See you then. Have a good day. Goodbye.